Hello, welcome back to the second part of my talk. In this part, I will show you how in practice one can use Pyiron to create and manage their workflows. In this part, all you need is your web browser and you don't need to install anything. And since this video will be accessible to public and can be used in public, we will use a public resource, which is my binder link, which is available in our GitHub repository for this workshop. Let's go to this link, and then we will see how you can go to this link and go to my binder.
I have to make a pause here. The link in the previous slide had a typo, and there was MaterialDigital missing after github.com. So here's the correct link. And also, if you are a member of Plattform MaterialDigital and you want to use the central server for Pyiron available to MaterialDigital members, please contact Dr. Flegel via info@materialdigital.de.
Okay. Here I am in GitHub and in the MaterialDigital organization and in the PMD workflow workshop repository. The link will be available in the description of the video on if you are watching this video in YouTube. And when you scroll down this first page of this repository in the README, you can find the my binder link. If you click on this link and open it in a new tab, this will take a few minutes to open up and lead you to the Jupyter environment. The first thing that I want you to do is to change this this ending tree to lab, so we can have Jupyter Lab environment, which has a slicker look and better customization. Okay, good. We are now in our Jupyter Lab environment, which is configured for our workshop with the right environment and everything. So all the folders and the notebooks are numbered, so you can start with this. I will start with this 0th notebook, which is an opening notebook. Here I have provided you some introduction to Jupyter Lab environment. I will not go through it because it's not the purpose of this workshop to make you familiar with Jupyter Lab or something, but I will show you the essential which is required for this workshop. In the first, you will see the content of the notebooks that we are going to talk about and use them, and you will see the different features of Jupyter Lab. But the most important part is that Jupyter notebooks in general consists of some cells, and you can write some code in these cells and execute them. And for executing them, you need to use one of these three short keyboard shortcuts. The easiest one is, which I use regularly, is Shift-Enter, so which runs the cells and move to the next cell. So with this print, we have just print. This is PMD onboarding workshop. When you press Shift and Enter, this is executed, and the output is shown below. Okay, so with this, we are ready to move to our first notebook, which can be found in the first folder, 1_1 intro to Pyiron building blocks. If you go to this folder and open the only notebooks available in this folder, you will reach this notebook. I will close this notebook so we will have a right focus. This is these notebooks will give you a introduction to different generic features of Pyiron. We will use a LAMP simulation, but as I will show you in practice, these are some generic features and can be used for any type of simulations. So let's, without any further ado, let's dive in to creating our first workflow using Pyiron. The first step is that we will import some modules, NumPy, which is a useful library for array mathematics, and matplotlib, which is the module for plotting and visualization of data. First, we execute them via Shift-Enter, and then we import from Pyiron atomistic projects. We are now interested in using LAMPs, and LAMPs is a part of LAMPs class, is LAMPs jobs, basically, are part of our Pyiron atomistic module. So we will import our project. As I mentioned, the project is the frame of our building blocks. All the components will come and sit on top of this frame. And then the first element that we need to create is the project. So basically, we will need to create a project object, and I want to show you how you can see what is the documentation and how we can use these functionalities and how things are done in Jupyter notebooks. The very useful keyboard shortcut is Shift-Tab, which shows you a docstring, which is basically some documentation or help of the function that you are going to use. So this project object needs a path and some other optional arguments. So we need a path to give it. So that it is a relative path, and we give it. We call this. You can call this project whatever you want. I will change the name of this this project to demo, for example, the initial demo, and then you will have this initial demo created. Just press Shift and Enter. You will have it. Since we are going to have a LAMP simulations, what is needed for a molecular dynamic simulation is a atomistic structure and some other parameters. So the first thing that I'm going to create is a structure, atomistic structure. Simply. Let me show you some interesting features of using Jupyter notebooks and Pyiron modules in general. If this has an auto completion. We have project and our project object PR, and then you can simply Shift Tab and you can see several options available. So if we say PR dot and then press Tab button, you will see the different options available for this project object. So I will click, I will choose create, and then again dot, and then you have different other options. So we can create a job, we can create a structure, or create a table. So I will choose a structure, and then we will see what are available. We can use ASE bulk or ASE in general, and then ASE is the package that Pyrion use, is one of the packages that Pyrion use for creating atomistic structure. And then let's see what are the available options. So we want a bulk sample. We will choose. Let's see what is the required what are the required arguments for this function. So we need, let's see, you can see that you need a name, which is a chemical symbol. You can name different, and then you can say whether it is a cubic or not. Let's try this, that we want an aluminum structure, and then in cubic is the option that we can put to true. So it will return us a cubic structure of aluminum. As you can see, this returns some aluminum atoms with a certain positions, and a cell which is periodic in all direction, and the dimension of the cell, basically. In this line, I will assign this structure to a variable called name, which is basis. And then we can also visualize this basis. How does it look like? So basically, I can type basis, and then we will get the same representation of this basis structure. And if I create a new cell, I want to create a new cell. I want to create this here rather. Okay. There is a shortcut, but I want to show you how to do it with this menu. So you can move to this cell and press this plus button. It will insert a new cell. So I want to plot this, visualize this atomistic structure. One of the, let's see what are the functionalities. We have different functionalities, but one thing that we are interested in is the plotting function. I have moved so far. Okay, plot 3D. Let's see what are the help of the function. Tell us. There is no required argument for this, so I will just print this basis plot 3D, and you can see you can simply visualize this, or yeah, good. And now let's move to the next. So we want to so we have this, we have created already this cell. We want to replicate this this cell in all 3 dimensions by 3 by 3 by 3 of the same structure periodically put together, and then we will also visualize this. A nice feature of Jupyter Lab is that you can create a new view for the output of your, I want to create a new view for the output. And then you can drag this to somewhere, for example, here. I want to create it here, and I will repeat this function, and you can visualize this here in a separate view. Yeah, exactly. This gives you a nice environment for your visualization put in this in a separate window, and you can do the coding in another window. Okay. The next step of our workflow is to create a LAMPS job, which is basically defining for a project for this as a part of this project. We create a LAMPS simulation, a LAMPS job, basically. The only thing required for this job is the to give it a name, and we are going to simulate aluminium with a temperature of 800 Kelvin. So we give this name. I will open a parenthesis here without making. I don't want to make this project a little bit complicated, but I want to show you how the thing that we are describing here are generic, and they are generic terminology. We can create another job like the same way that we did here. So I will open new notebook to show you that what we do here is similar to, we can do it similarly for another simulation tool, for example, for Continuum simulation. I will, from now, I import from Pyiron Continuum, and instead of Pyiron Atomistic, I will import from Pyiron Continuum, import a project here. And then we need to define a project object. As you remember from the other notebook, we need to just define a path, a relative path maybe. Here I put Continuum demo as the name. Now, in the previous case, we defined the job for an atomistic simulation, but here I want to show you in a similar fashion you can create a continuum scale simulation. Here I will use Damask job. PR, similar to the structure, we say create, and it's here job, and then you get a different option. You can you can use Phoenix, Damask, Phoenix, linear elastic job, or some other job. But I will use Damask job. Let's see what are the required. Basically, you need to give a job name for this. Let's say job, and then you give it a name. Damask example, for example, and then by pressing Alt and Shift, it will execute it and create a new cell below it. So you can see that I created a job in a similar fashion and similar terminology. We are using, instead of lamps, we created a continuum scale simulation. Similarly, you can have a second job, PR create the job dot, for example, Phoenix, and you give it another job name equal to Phoenix example. You can see similarly you can have you can use a same terminology and have a common platform for various simulation. And within one project, you can have multiple jobs and simulation and analysis of experimental data, even in the same project, as I will show you in our following examples, that you can have multiple simulation analysis in the same projects. So this was a parenthesis that I opened to show you the common terminology and interoperability of the of Pyiron. So we created a LAMPS job, and we gave it a name, and we want to assign the structure that define a structure that we created here to this job, as the job has a member, has a variable called structure, and then we assign the created structure to this structure attribute of the job object. And then later with the calcmd here, we give the temperature, pressure, and the number of steps for our MD simulation. Simply we execute this, so, and we get job. And since we have given the structure, the job knows what is the composition of your sample, so, or your system. So you can see what sort of atomistic potential are available for this for this composition. You can select from various potentials available for aluminium. So we will choose basically the first. This least potential gives you an array of potentials, and we choose the first element of this array. I will show you basically what this job list potential return for you to see that this will gives us an array, a list basically, and we choose the 0th element of this list, and we assign it to the potential attribute of our job. As I mentioned in my first part of the talk, you can simply assign the number of cores, and also the server queue that you want to send it to a remote cluster. But here we are using my binder link, and we are not having a multiple cores to run these jobs on. So I have commented them. So basically, but you have the possibility, if you have configured your server to connect to a HPC cluster and submit your job there, you can assign this queue, core, and a runtime and other parameters, and then by job run, it will be submitted to the cluster. And basically, we hit job run, and we get our first simulation done. In the next step, we would like to analyze our calculation. You can basically I want to show you how Pyrion use here you can again, you can assign the job by going through the a semantic path and assign the job to if you want to the same aluminium, and basically the given name that we for our job. Before doing that, I'd like to create a new cell and show you that what are are available for our job. And you can see that basically you can assign the job differently with a semantic path. You get similar output from the job. You can basically, via this semantic path, you can explore the job, your job. I want to go to input and see what are available in our input. And if I go to generic, for example, what are the, okay. And let me go back again. If, for example, control input, we can see control input. What are the available, what sort of inputs we have for our, but basically we are now interested in our output. So similar to input, you can access output with semantic path, and then you can see that in our output you have different parameters: cells, energy, potential energy, total energy, forces, position, and everything is stored. A nice feature of our job is to animate the structure. I mean, that you can see basically via an animation the trajectory of the particles. We can see that you can see within your notebook you have the animation of your whole simulation. The next step is that we want to visualize a temperature evolution along, as our simulation has been performed. Let's see how you can access this temperature via semantic path. Here you can write similarly job output, generic, and then we will see that in this output generic you have your temperature here, job. Again, I will copy and paste this to do not repeat it, and then temperature, and then you see that you get an array of temperature, and we can have also we want to plot it as a function of time, that during the simulation how the temperature is evolved. So in the next cell, I have assigned this temperature array to a variable of type list, of type number array, basically temperatures, and then steps, and basically via our matplotlib module, we want to plot it. We give it X label and Y label simply, and we create our plot simply like that. Easy. Within all what we have done is performed within our notebook. So the first exercise for you is how to access the position of the particles. You can have this guess that now we access, basically position is one of the outputs, am I right? So you can maybe guess that position can also be a part of job output of the job. So what can be the correct way to assign what's the correct way to get this positions of particle from our output. So if I guess you can have guessed this from the previous step, that you simply output generic, and then let's see what are our output generic. Okay, we have unwrapped positions, but we are interested in wrapped positions. If you are from atomistic simulation groups, you can't guess what's the difference between unwrapped and wrapped positions, but it's out of the scope of this this workshop. So basically, we get an array of the positions. Each particle has a tree X, Y, and Z, and it goes on. And we want to assign this to a variable called pose, and then simply we will have this, and then with this in this plot, in abstract, I want to tell you what this plotting function does. It plots the trajectory of particles in a layer confined between 0.1 and minus 0.1. So all the particles residing in this plane will have their positions plotted in this in the next plot that I'm going to plot here. So nicely done. We have the trajectory done. So far that we saw that we access our output and input via our semantic path. The next feature of Pyiron that I want to talk about is Pyiron GUI. Simply, we can access this output and input and of the job via our GUI, via Pyiron GUI. I prefer to also create a new output view and put it next to this. Okay, so you see that we have this job. We want to go to output. We have generic, and then simply we can say temperature, and it gives us the desirable temperature plot that we had before. If I scroll it back a little bit, zoom out, you can, for example, simply, plot also potential energy in a similar way. So you see that not only we have a coding view, we have some GUI elements also implemented so that people who are interested more in GUI applications, it can be used also. Of course, Pyiron always can get better as it is open source, and you can contribute to it. One can, for example, here in Pyiron GUI, produce a function which we can, for example, define the limit of this plot simply, as it's basically using matplotlib, and you can define a IPython widget, and you can basically write the x limits and y limits simply like that. And now let's go to the next part. In the next step of this workflow, we are interested in changing the temperature and observing what is the the effect of temperature, for example, on the volume of the our structure. So we need to define a series of jobs to calculate to run some MD simulations for various temperature. What I will do is that we define a for loop which goes through various. I will use the NumPy package in abstract. I have imported it as NP and I will have my temperature between 200 and 1200 with increments of 200. And then we define our job simply as before. Job create a project. Our project create that job and dot lamps. Okay, and we give our job name, basically job name. And then this job name would be, I try to give it a name, a meaningful name, F, and we have similar to the previous case, aluminium and temperature as our given temperature. Yeah. And we have our job structure simply equal to super cell the structure that we defined before. Job dot potential, we define a potential attribute to the potential, and the type of the simulation. We have an MD simulation for lamps temperature equal to temperature, and pressure. For the pressure, I will give zero, and for n ionic steps we define 10,000, and simply job dot run. I hope I haven't made a mistake, and then can run this. One thing, because I want this to be consistent with the previous job that we had. We had aluminium. The definition of the name of the job was aluminium and T800. And here we have I use a F string for the job name, temperature, and then you can search for the formatting of this. If this is a F string, you can simply find it. Okay, now we are running multiple jobs for various temperature and for the same composition and structure. And interesting thing here I want to emphasize here, that's job aluminium T800 Kelvin is loaded and it is not rerun. So basically you can see that since the job has been performed once before and the status is finished and the job succeeded completely and saved, it is not rerun. So it is loaded instead of rerunning. So now our project has multiple jobs with MD jobs with various names and different temperatures. One thing that I want to mention here now is that all this this output, this semantic paths that we use for output and input is the benefit of Pyiron using HDF5 files to store the inputs and outputs of our jobs. So you can see for each of our jobs, there is a HDF5 file, a binary file is created, which can be used to access our job data, the input and output, and other control parameters stored in these files. So this was a quick comment that I want to mention, that our job data are stored in our HDF5 files, and they can be accessed via the semantic path that I showed you before. So let's go back to the to our job. Here we want to plot the volume and temperature of our basically our a mean temperature and mean volume of our of each of the jobs. So we will go through all of the jobs, and we store the volumes. We have, yeah. Let's, before doing this, let's see what sort of what are these job output volume and what are this job temperature. You see that for volume you get a number of volumes for each of the sampling steps. So for one simulation, we want to average it over a number of these volumes. So we get the volume and temperature for each of the jobs. We append them to a list. Then we will get an average of them, and we will put them in a list. So now with this for loop, we got the volume, the average volume and average temperature of each of the of our I guess it was 1, 2, 3, 5 simulations. For our 5 simulations for aluminium with various temperature, we will get the volume and the temperature. Here we sort this volume and temperature, and we want to plot them. You see that with this we got the thermal expansion of the our sample, aluminium sample with a given potential. Now, now think that you are done with your atomistic simulation, and you want to share your workflow and the jobs with another colleague. For example, some guy who wants to use your simulation data to perform a continuum scale simulations. What is the what can you do to share your data, your jobs and everything? Pyrion gives this functionality to you via packing and unpacking of a project. Pyrion stores the metadata of each jobs and the projects in a central database, and you can access this metadata from the job table. So within our project, we have the I will, for now, I will close this these secondary views, and let's have a full screen of this job table. You can see that we have number of jobs, 5 jobs in these projects, and each has their name, path, and the time and CPU time and everything, the lamps type of simulation, and it's stored in the job table. What does this packing function does? It stores this job table in a CSV file, and also it compress the HDF5 files of our simulation to a tarball file called lamps project. So if I perform this and we go to the Explorer and refresh it once again, you can see that we have this export CSV created and a tarball file of the. You can open this and you can see that the exported CSV contains basically the job table of our project. So basically with this you have all the necessary data from your project to be shared with another colleague. So I will go to the next notebook, which is stored in another directory. We were here in the 1_1 intro Pyrion building blocks, and I will go one step above and 1_2 import project directory, and I would like to open this notebook. I have copied and pasted the CSV file and the lamps tarball, the lamps project tarball file, and here in this directory, and I open this this new notebook. I will save the previous notebook. Okay, similar to the previous case, we import. We want to create a new project. We import from Pyrion Atomistic project, and we create a project object called imported project, and we want to use unpack. If you are not familiar with the unpack function, you can simply use the keyboard shortcut Shift Tab to see the Docker string. You need the origin path, CSV file path, and the compress. If this is an optional to check if if your exported project is compressed or not. So we give the CSV file name and the path of our compressed project, and we unpack it. Now you can see that we have unpacked our shared project in a new project. So let's inspect that if our new project contains our imported jobs. Okay, it contains the first group. Let's go to pr.job table. And you can see that similar to our previous job table, we have imported all the jobs, and the status are finished. And a good point is that since the database of the Pyiron is central. The ID of the jobs that you imported are added to the previous. It's incremented. So in the previous notebook, if I reopen it, here you see that the job ID was go down, was from 1 to 5, and here you see that it is added to the database with the new ID and new path, and you can see that we have imported the same jobs in a new project. An exercise would be to use Pyrion GUI to plot the temperature of the same temperature plot that we had for the first job, for the yeah, I guess we plotted here, yeah, the temperature. We want to create the same temperature within the imported. So pr.gui, and then we will have our first step, and we had this OLT 800 output generic, and the temperature. Simply, you can see that we got the same. So you have with this packing and unpacking functionality, you are able to share your not only your project, but all the results and data, and at final latest stage, you can export it and share it with another colleague, and the other colleague can continue from where you left, basically. This gives you a great possibility for collaborations. So now that we are done with this notebook, we will go to the next notebook. Let's close all this, save them. Okay. One thing that I want to show you in the Jupyter lab environment, you have all of these notebooks have some kernels which take care of execution of your commands and the cells, and you can shut down all of them from this tab on the left. Here you have the kernel tab, and you can shut down that previously open. I want to just mention these features that can be useful to you later on. In the next step, we want to create some new workflows. We want to first create a new job type, new job class, assuming that you have a Python tool, and you want to implement a job class in Pyron to use this new Pythonic tool and manage your workflows, which involves this new tool. In these two examples, first we go to I will show you how to create a new job type based on the Python class, and the other one would be a job type, a job class based on a bash command. So let's first focus on the Python tool. Before talking about the details of this new job class, I want to mention again that you can document your workflow as you have the codes inside the workflows. You can also document your workflows. Here, if I click on this text that you were seeing, you see that this is basically a similar cell that instead of a code, this is a markdown, and you can write a text in this cell, and similarly you can execute this cell to represent it as a text. Here I have documented my workflow that if we need to repeatedly perform a combination of process to return a value, a plot, etc., it might make sense to create a job class for it. And here we create a simple workflow using available Python tools for a specific program. The problem that we here I've created job class for it is that we are given as an input the position of some particle plus their energy constant, and the goal is to calculate the mean harmonic energy and return a 3D plot of this cloud of particle. The assumption here is that all the particle has interatomic interparticle potential of harmonic nature, and they have all of them have pairwise interaction. So to create, as I mentioned in the first part of my presentation, we inherit from some generic Pyiron classes. Here we would like to inherit from a Python template job of the Pyiron base. If you remember, Pyiron base is the module we use for our workflow management. And from Pyiron base, we import a Python template job and data container. Data container is a data type from Pyron, which integrate all type of variables, sequential variables like dictionary arrays into and integrate them to HTML5 file easily. And this is a part of Pyiron base, and we import all this from Pyron, NumPy, and also Math and Matplotlib for visualization. As I mentioned, one of the goals of this workflow is to return a 3D plot of the cloud of particles. We define a class. You can see that we inherit this class from Python template job. We have the constructor of this class. We inherit the init function, the constructor from the, and basically we give a data container. We define the job input as a data container with a name called inputs. This data container has a read functionality, which gives us the possibility to read data from a file. If we here you can see that we are given a YAML file with an energy constant, equilibrium length between the particle, and the position of all particles. And so this read input function use the read functionality of data container to read the the data from the input file. The interesting part is that it directly, since we used this data container from Pyiron base, it directly stores this into our HTML5 file, and we do not need to specify it anywhere. So so in this function, we calculate the mean harmonic energy, and we have a plotting functionality implemented. And at the end, we run we have this run static function with this function. When this function is executed, when we basically press job.run, this run static function is executed, which first calculate the mean harmonic energy, and then the output of which is the average energy is saved in the HTML5 file, and then the status of the job is when it's finished, it's this set to true. So the first exercise is that we would like to create a project, a job type of type harmonic energy, and which reads the input.yaml file and calculates the mean harmonic energy, and let's click create. So let's start from importing project from Pyiron base. I import project class, and then I define a project object called harmonic project, and we define a job. We have project here. Since I have not implemented a refractory for job create, we cannot use since you need a new class for defining this pr.create.job and harmonic project. Since we have not implemented this here, we can use use it differently. We use this create job function, which you can see the documentation. Also, you need to give the job type, job name, and then you're done. Create job type. For job type, we are now defining this. We have defined this harmonic energy job. So I will use this job as our job type. And for the job name, I have a harmonic job. And then oh, sorry, I have not executed this, so it's not. So now I can execute this. Perfect. Now I need to give the input job.read. We had this read input. You need to, if I have not given any doc string, if you want to give a doc string, you can simply go to the function, give the doc string for the, you can say that read and input file arguments is that it is file name of type string, the path to the file name, to the input file. If we execute this, and I go to this and press Shift Enter, job.read. Unfortunately, it has not recognized. Let me re-execute this. And again, read input. Still, I don't see the doc string, but normally you should get the doc string here as you press a Shift tab. And here we know that you need to get the file name equal to our input.yaml file. It's a string input.yaml, if I remember correctly. Input.yaml, exactly. And then press, and this is done. And if I want to create a cell, and then we can job.run simply, and this is okay. This job is done, and you can see, and we want to see the calculated harmonic energy. Let's see what is stored in our output. Generic, similar to the previous workflows. We have output generic, and here job output generic, and then average, copy and paste it here. You see that you get the mean average, the mean harmonic energy for this cloud of particle. Now, one of the goal of the exercise was to plot this job. What are the functionalities of this job? Plotting, maybe, no, scatter, maybe job dot scatter, yeah, a scatter plot. What sort of, I don't have any doc string for this. Now I can look above. There is no no argument needed for this. Job.plot, and you can get the 3D plot of this cloud of particle. And I guess for this I have done this. So the exercise 2 is done basically in here. Via this, you can get the. Before going to the next notebook and the next part of our hands-on session, I would like to show you where you can find the complete notebooks. If you go to the workshop repository in GitHub, you can find this link. I will put it also in the description of the YouTube video. You can see that all the workshop notebooks are here. For example, this integrating a generic Python tool in Pyiron is has here all the required answers, and I mean the answers to exercises are included in these links, in this link available here in the repository. So by looking into different part of this Jupyter book, you can get the answer to the exercises. The links will be included in the description of the YouTube video. Let's go back to our notebook. I will close this. I will save this and close it. Let's go back to our file explorer. We have this. Now we were looking at a custom Python job. Now we want to look at the custom Bash job. This wants to show you how you can integrate a new tool, whether it is a Python, whether it is some Bash command, whether it is some C codes and some executable from your C code or C++ code. You can do this via Pyiron. So basically, you need for this workflow that here I have brought. You need to inherit from generic job from Pyiron base, and we need some generic parameters for the input of our job. We have a toy bash job which gets some generic input. Our input is input energy, and it is similarly, we basically for our job to be executed, we need to give it executable as a string. You give the cat input to the output. Basically, it puts all the text from input file to some output file. Here, if you were interested, you can, for example, replace this. I will not do this, but basically you can replace this with some other executable. For example, you could replace this with self.executable. Let me put it in the next line. It would be clear. Self.executable equal to my executable and some, for example, some input and your input file, and then you get some output file. It could be anything, any commands and any executable that you are interested in. Here we have some additional functions which write the input, as we have some input energy, and we will put it in some input file. The file name is input, and then we since it is not Python a Python job, it's a bash command. You need some additional functionality called collect output and to HDF and from HDF, which takes care of putting your data in HDF file. And since you are now working with files rather than directly putting your data in the HDF5 files, which stores all the information from jobs in Pyiron. So you need some additional functions to do that. But the most important thing that, in my point of view, is that the most important thing is done via this self.executable attribute of the generic jobs of Pyiron. If I execute this, sorry, I have not imported this generic job. I have to both import this. And then the exercise one is to create a job of this toy bash job. Similar to the previous example, from Pyrion base, I import project, and then I create a project object, bash project, and then job equal to pr dot create job. You know that it needs 2 arguments, job type and job name. Job type would be our toy bash job here. And our job name is a string that we arbitrarily define. And if we press job.run, this will be executed. If I look at the job, we have some input and output. Job.input. If I look at this, job.put, I guess this is input and put. Okay. It's generic. Make this yeah. But you can also access the output of the. Since we have not defined all the restart file or anything, there is nothing stored in the this dictionary. Output generic. We have this job. Copy and paste it, not to. And then we have the energy total. And yeah, that's it. We have everything is stored here. Let's look at the job table. Also, for this new, we have also some job table that you see. That's this is of toy bash job. All the metadata for this. There is no chemical formula, of course, but the status is finished, and we have all the metadata, the path, the CPU time, and everything is stored in our job table and our central database. Now, with these 2 notebooks, we showed how we can import, we can implement basically 2 new workflow classes in Pyrion. One based on a Python workflow and Python tools, and the other one is basically on a arbitrary executable. Here we use some bash commands. You can use some executable from your C source code or something. So let's move to the next notebook after a short pause. Okay. Before moving to our next notebook, I would like to recall you of this shareability functionality with my binder link. If you put your Pyrion notebooks along some environment and some additional file in a public Git repository, and you want to share your workflow with some other people. You can share it publicly. You can, like what we do in our Pyiron website, you can see in our publication alongside the publication, you can find the My Binder link, which leads you to an environment to execute the code, or at least parts of the code which can reproduce the results of in the publication. So this is a nice feature that Pyiron workflows can provide for shareability of your workflow alongside your publication. So let's go back to our Jupyter Lab environment and go to the third part, which is a LAMPS Damask workflow. In this notebook, the goal is to calculate the macroscopic response of an aluminum magnesium alloy based on the atomistic properties, atomistic elastic properties of the these alloys. So here we have a combination of atomistic workflow and continuum scale simulations. So in the first part, we calculate for a set of concentration of aluminium and magnesium the elastic properties of the samples for quasi-random structure. We call them in Pyrion SQS elastic constants jobs. And then based on the output of this, which is a polynomial fit of the for the elastic moduli as a function of concentration of magnesium. Then in the second part, which is the continuum scale simulation, we will use Damask as our solver for continuum equations of conservation of momentum. We will feed we will feed our feet as a model for the elastic properties to our inputs of Damask. We define a geometry, a loading, and solve the equations, and we will post-process the data, and finally we will visualize the macroscopic response of this aluminum magnesium alloy based on the elastic properties from the atomistic simulation. Here you can see the two workflows coupled. We have the atomistic part, which calculates the elastic moduli and the feet, and then this feet will be fed to our Damask workflow, and then we will get the macroscopic behavior of the material. This SQS elastic constants job is based on the created quasi-random structures of different compositions for aluminium and magnesium, and then based on these quasi-random structures, for each of these structures, a set of deformation is applied, and based on the response of these structures, the elastic constants for a specific composition is determined. First, we will import the required modules. From Pyiron Atomistic, we have the projects. We import Pyiron Continuum for our Continuum simulation, NumPy for our array arithmetic, and Matplotlib for plotting, Seaborn also for plotting, and YAML for dealing with YAML files, which is required for Damask simulations. Sorry. We will create a project. It's interesting that all of our projects, whether it's atomistic and or Continuum, they are included in the one single project, which we call it now Elastic Pipeline. We first minimize the energy of a cubic cell of aluminium. We create a LAMMPS jobs. We calculate and minimize the energy of this structure. This will gives us the minimized structure for this cubic cell of aluminium. Then we will feed this structure to the next jobs, which is of type of SQS job. This will create our quasi-random structure based on various composition of magnesium. By running this, we will get this quasi-random structure. We will assign this for pure aluminium and 0.5% magnesium, 1% aluminium, and 1.5% magnesium, and 2% magnesium to this concentration list. We will get the structure list from the output of this SQS job. You will see that the chemical formula of all of these SQS jobs. We have 5 set of jobs from this SQS job, so 5 set of quasi-random structure, and then this quasi-random structure are fit to our elastic matrix jobs, which apply the underneath apply a set of strains to this quasi-random structure and calculate the elastic moduli and the elastic tensor for all of these quasi-random structure. This will take a few moments to finish. Then this will take a few seconds to finish. For in the next step, we have all of these jobs which calculates the elastic constants for various compositions are determined. In the next step, we need to get the elastic constants, the elastic moduli from different jobs. Now that the jobs of the previous step from the elastic matrix job are over and finished, let's look at the job table. If we pay a close look, we have if we move to if we look at the job table, you see we have various jobs of different job types in this stored in this job table of our projects. So we need to get the information from these elastic matrix jobs and to get the concentration, to get the elastic moduli and elastic tensor for various concentration of magnesium. So it is required that we get from our job table, we get the jobs that are of the type of the elastic constant job, elastic matrix job, and we need another functionality to look into the HDF file of each of those jobs to get the elastic constants from those jobs. So we need two functionalities: looking into metadata of all the jobs and finding the jobs of the type of the elastic matrix job, and the other one is we look when we filter those jobs. Another function looks into HDF5 file of those filtered jobs, and then give us the elastic tensor for each of those jobs. So Pyiron has a special tool for this task. Basically, for data mining, we have Pyiron tables defined. Pyiron tables are based on two functions. One is the filter functions, which looks into the job table and then filters the jobs that we are interested in, and we have another functions to get to add the results that we are interested from the HDF5 files to this table. So we define basically our filter function to get the elastic constant jobs, and then we will get the C11 component and C12 and C44 component of the elastic matrix from the result of those calculations to our table. So basically, we will first create this table based on the project create table, creates this Pyiron table for us, and then we define the filter function, which we defined here, and then we will add C11, C12, and C44 based on this this function that we added. This get C44 is basically look into HDF5 file, the output elastic matrix, and the elastic tensor and the element the element of this elastic tensor tree, which represent the 4/4 component of the elastic tensor. Then table run, which filters the job and gets at this C14 and this basically the component, the desirable components of the elastic matrix, and then we can create a data frame based on this table, the Pyiron table that we created. So for each of the job, we now have we had 5 concentration and 5 jobs and 5 elastic moduli for each of the components of the elastic tensor. So we can now fit a polynomial based on the concentration and all these results of our atomistic simulation. Let's first we define a concentration array. We convert basically a concentration list to a NumPy array. For our feed, we have the this data from this data frame converted to also to some NumPy array, and then we will feed a second order polynomial to this data. We get the feed, and we can plot this feed to this elastic constants for different concentration of magnesium in this aluminum magnesium alloy. Now we reach to the second part of our workflow, where we have the Damas calculation. We can give multiple concentration and calculate the macroscopic response based on those concentration, compare them. But for the sake of time, and since these calculations are a little bit more time consuming than the time limit of these hands-on sessions, I will remove the second element of this concentration sample list, and we will only calculate the macroscopic response for only one concentration. And then we have some predefined YAML file for the geometry and the material properties, and then we have the load definitions. We will import those, and in the second in this part we will define our jobs. Here you need to define a job based on each of these projects. If you look at here, these jobs are appended to this list. So we will define job, project, create a job dot Damask job, and then we will need to give this a job name, and here I will use a sensible name for our job. If I recall, if this is not important, we can have aluminium, magnesium, and then you can have I will put it as the concentration for the and then here we have the job defined, and then we need to we have input as an input 2 components of the also elastic constants and elastic, but the third one, which is C44, is missing. Now we can have it's as C44, and then we can have job.run, and then our Damas job is also okay, sorry, the names that I have chosen. Okay, I think I should give it an int multiplied by 100. Okay, this will take a few minutes to finish this Damask job. I will pause the video and we will return after this job is finished. Now our Damask job is also finished. You can see that it is saved and our kernel is now idle again. If I look into on my job table again, project job table, you can now see that at the end we had a table job. Now we have a of aluminium with a 2% magnesium alloy as the name of the job, and the type of job is also a Damask job. Now let's go to the next part, which is a post-processing of our Damask simulation. The result, we will calculate the von Mises stress and the equivalent strain for the von Mises stress. These are rather quickly calculated and processed. Now we can visualize this. We have here in this table, we have the information of the mesh of this continuum simulations, the number of cells, number of points, the fields for stress, von Mises stress, and the equivalent strain for von Mises stress, and we can also, in principle, we should be able to have a 3D plot of this for this simulations for this continuum simulation. But recently, with the latest update of PyVista, this Jupyter Lab extension does not work anymore. I will show you in a few minutes this in Jupyter Notebook environment. And then we will see this, how does it work, this 3D plotting of the, but let's, beforehand, let's see how this macroscopic, I guess this is, okay, this is, I have to comment this out, and then we will see the stress strain plot of magnesium, of the 2% magnesium, basically. There's 2% magnesium, then we get the macroscopic response of this 2% magnesium alloy, magnesium aluminum alloy, to a tensile load. Let's go to have a look in if we copy and paste this this link, and then I want to add 3 to this, to the end, to go to the notebook environment rather than Jupyter Lab environment. Go and open again this notebook. If we go down, as I mentioned, this Jupyter Lab extension for PyVista is not working anymore. Now I will try to make this plot in the notebook environment, Jupyter Notebook environment. And okay, now we have this 3D It's a little bit hard to. Okay, now I could control it. We can see now we are displaying the displacement of each node. We can check the strain, the stress sigma, the strain. We can visualize the 3D plot of the stress, strain, and we can have von Mises stress and the equivalent strain to this von Mises stress. Yeah, so you can see that based on the this module is not very friendly with my mouse. So basically, okay. No problem. Anyway, so we can also have a 3D visualization of the post-process data from our continuum scale simulations. So with this, we came to the end of this workshop. There is also additional material available as for data mining. You can go through this notebook on your own. It's all described and documented. So we had a data mining part in our LAMPS Damask workflow, where we got the elastic constants from our elastic matrix jobs. So based on this, I give you the chance to go to this data mining notebook on your own. I hope that you find this these tutorial sessions useful to get to know more about Pyiron, and I hope you get to using Pyiron. And if you have any issue or a question, you can contact us via GitHub or Stack Overflow, and we would be happy to answer your questions. I mean, me and my colleagues from MPIE and our GitHub repository, our GitHub organization, we will be certainly happy to help you to get to know Pyiron and to help you to use it. Okay, have a nice time and see you in other meetings.